This organic chemistry video is going to be about the structure of benzene and the evidence that surrounds the subject on the actual structure of benzene. First of all, I'd just like to talk about the representations of benzene. There are two different ways of doing it. One way is called the AQA model, where you have these resonance structures flipping back and forth with the movement of electrons similar to this, and resonance structures show there's actually an average structure of that in between them. So you can represent it as either one of these, or you can represent it like this with a hexagon with a circle in the middle. And these are both skeletal formulas. So let's actually look at the structure of benzene. First of all, if you don't know what a pi or a sigma bond is, please refer back to my bonds and alkenes video, as it tells you the bonding in an alkene, and that's very similar to what we're going to talk about in benzene. So benzene has these sigma bonds between each carbon, 6 carbons in a hexagon, and each of these carbons have a p orbital coming off them. If you remember, in alkenes, you can have a side-on overlap of p orbitals between carbons to form a double carbon-carbon bond, and a pi bond is one of them and the sigma bond is the other. Well, we can have the same kind of thing. If we look at this AQA structure down the bottom here, one of the resonance forms, it shows a double bond at the top and 2 at the sides. That would indicate you've got electron density shared there, electron density shared there. These p orbitals would also overlap to form pi molecular orbitals, a bit like that. Well, this resonance structure shows, well, there's double bond there, and double bond there instead. Well, that's because why should the p orbitals only overlap between those 2 carbons, those 2 and those 2, when the p orbitals are identical length between each carbon, like say that is length x, that's also length x, they're identical. Why don't they all overlap? Well, in fact, they actually do. We get an overlapping of all of the p orbitals with all of the neighbouring p orbitals. So instead of the 2 electrons in this bond being shared between this carbon here and this carbon here, it's actually shared across all 3 carbons. So it reduces electron density a little bit, but it makes it more stable as the charge is spread across the whole thing. And this is called the delocalized pi system, because the electrons actually delocalize and form an electron cloud above and below the carbon nuclei and the sigma bonds. So you kind of have something that looks a bit like this. If this was a side-on view, you would have your sigma bonds in a hexagon, and then you would have this sort of cloud above and this cloud below, which are the p orbitals that have delocalized around the entire molecule. Let's look at some of the evidence that supports this. Why do scientists think that benzene has a delocalized pi system, sort of kind of an in-between of not one bond between each carbon, not 2, but somewhere in the middle? Well, if we look at the bond lengths, we have a carbon-to-carbon bond has a certain length, which is 1.54 angstroms. If you don't know what an angstrom is, 1 angstrom is equivalent to 1 times 10 to the minus 10 meters. It's a handy unit for chemists, as certain bond lengths are very close to 1, and yeah, it's just handy to use really, rather than nanometers or micrometers and stuff like that. So if we look at a carbon-to-carbon double bond, that's 1.34 angstroms. And now if we look at the benzene carbon-to-carbon bond, I'm going to represent that by a solid and a dashed line, as it's kind of like in the middle of a single bond and a double bond. That's 1.39 angstroms. So that indicates the delocalized model is right, because the electrons aren't just confined between 2, they're confined sort of between 3 molecules, making kind of almost 1 and a bit bonds. It makes them a little bit weaker because the electron density is a little bit weaker, but overall it makes the molecule stronger. Now when we look at bond lengths, there's something called X-ray crystallography, and that basically fires X-rays at a crystal structure of benzene or another molecule, and the X-rays scatter, and a computer program can pick these X-rays up and sort of look at some complex maths, put them back together, and it can actually piece together the shape of the molecule. And what we find is we get a perfect hexagon. Now, please forgive me, this won't be a perfect hexagon because I'm not an artist. We get a perfect hexagonal shape. Now, if we had a combination of carbon-carbon single bonds and carbon-carbon double bonds, what we'd get would have, say, short bond here, long bond, short bond, long bond, short bond, and long bond, representing the double and the single carbon bonds. That's not right. That is not a perfect hexagon. That is horrendous. And that's not what we see. We see this perfect hexagon, which means the bond lengths all have to be identical, don't they, to get the same length on each side. And that is what X-ray crystallography shows, along with the bond lengths. And that's the first piece of evidence. Well, kind of two pieces of evidence, bond lengths and X-ray crystallography. Let's look at the second piece of evidence. Well, this is reacting molecules with hydrogen. Now if we look at cyclohexene, which has one double bond, and react that with hydrogen in an addition reaction, that will go to cyclohexane, and that has an enthalpy of minus 121 kilojoules per mole. Now if we look at benzene, if we just write it down as the AQA structure, or one of the resonance forms, and we react it with 3 lots of hydrogen in an addition reaction, we get cyclohexane with an enthalpy change of minus 208 kilojoules per mole. Now that's a bit odd, because we think, well, if we're representing it as 3 double bonds, surely it should be 3 times that, and minus 121 times by 3 is not minus 208. A young child could tell you that. It should actually be minus 363 kilojoules per mole, as that's what 3 times minus 121 is. But we don't. It actually turns out that benzene is 155 kilojoules per mole more stable. And that's because of that delocalized pi system. It just makes it more stable because the electrons are spread out everywhere, and it makes it harder for like the hydrogen to attack in and things like that. And like I said, it's just a lower energy state. And this is the second piece of evidence for that. Let's look at the third bit of evidence. Well, benzene is resistant to addition reactions that would spontaneously occur in alkenes, and it prefers to undertake a substitution reaction. So we look at an alkene, carbon-carbon double bond like that. I'll ignore the hydrogens or any R groups, and we attack it with, say, HBr. That will, without a catalyst, that will break that bond, add a hydrogen in one and a bromine in the other, and there's a nice little addition reaction. Benzene doesn't like to do that. Benzene likes to do something called substitution. So again, I'll use the AQA structure for it, and we'll talk about this hydrogen here. I've done the skeletal formula set for that hydrogen just to demonstrate what happens. And you react that with, say, bromine, and it requires a catalyst, then you actually get this structure here, and the catalyst would be something like FBr3 if you were reacting with bromine. Well, a catalyst is required because it's a lot more stable than expected, and as you know, a catalyst lowers the activation energy of a reaction. Now the reason why it doesn't do addition reactions is because this pi system, this delocalized pi system, is very, very stable, as we established in the previous slide. And because it's so stable, it wants to reform it. Obviously, to react it, it's got to break this pi system, which, if you watch another video that I'm about to put on the next slide, it will show you how the pi system is broken. But it likes to reform it because it's just a lot more stable. These delocalized pi systems are more stable than having 1, 2, 3, 4, 5, 6 extra single bonds in there, like a carbon to bromine, 6 extra bonds. It doesn't want to do that, and the electron density is a bit lower because it's a mix. Instead of a highly dense carbon-to-carbon double bond, it's kind of like a 1.3 kind of bond, if that makes sense. So the density is a little bit lower, so it can't polarize this Br2 molecule like an alkene can if you reacted it with Br2 instead. And yeah, so you just look at the stability. The evidence is that it doesn't undergo these addition reactions, it undergoes substitution instead, and that's your third bit of evidence. Now that's the end of the structure of benzene. However, please watch the electrophilic substitution video for benzene reactions, such as reaction with Br2, Cl2, and one of these structures here where you have a tertiary carbon with a chlorine coming off or something like that. Please watch a video on that, as it will help you throughout A level, and you can look at the mechanisms for the substitution instead of the addition. Please share this video with friends if they're struggling on a similar topic. Thank you for watching. Please subscribe and like for more videos. Let me know if there's anything you want me to cover that I haven't already. Thank you.